Hello and welcome back to the deep dive. I want to start today by asking you to do something very simple. Wherever you are, walking the dog, driving, sitting at your desk, just stop for a second. Take a deep breath in through your nose.
Go on, actually do it.
Yeah, really do it. Fill your lungs all the way to the bottom. Hold it for just a beat and let it out.
It's satisfying, isn't it? That little release.
It is. It's effortless. Automatic. You don't have to send a memo to your brain or, file a request to make it happen. But here's the thing. That simple act is the result of the single most dangerous, complex, and frankly miraculous physical event you have ever survived.
And we're not being hyperbolic here.
No, not at all. And I am not talking about a car crash or a major surgery or running a marathon.
No, you're talking about the day you were born, the first few minutes, really.
I am. We tend to think of birth as a change of address, right? You move from the inside to the outside. It's a relocation. But today, based on the research we have in front of us, we're going to find out that birth isn't just a move. It is a complete, total rewiring of your entire internal engineering.
It's a physiological overhaul, a complete system reboot. And the wildest part, it has to happen in minutes, not hours, not days, minutes. If it fails, life doesn't start.
That is the stake we are playing for today. We are stepping into the role of a medical professor and a senior consultant. We're going to conduct a kind of masterclass on the mechanics of taking that first breath.
Right. We're going to try and strip away the complexity to understand how a human being actually turns on.
And we're doing this by doing a deep dive into a specific foundational text, Cardiopulmonary Changes at Birth and Principles of Newborn, by Dr. Kenechukwu K. Ilo.
And this is a serious piece of work. It's the kind of text that informs clinical practice.
Absolutely. And just to set the stage on credibility here, Dr. Ilo is a heavyweight. We're talking MBBS, Fellow of the Medical College of Pediatrics, Fellow of the West African College of Physicians. This isn't a blog post. This is high-level medical literature.
It's the kind of text that dictates how doctors actually treat babies in the delivery room. It's the roadmap for those first critical moments.
So our mission today is to answer one fundamental question. How does a fetus, which is essentially a submerged creature living underwater with collapsed fluid-filled lungs, transform into an air-breathing mammal instantly?
It's an engineering marvel. There's really no other way to put it. It's one of the most violent and beautiful transitions in all of biology.
Before we get lost in the weeds of the physiology, which we will, I want the elevator pitch. If we were stuck in an elevator with a first-year medical student who is panicking about their exam, and they ask, what is the core concept of birth physiology? What were the 3 sentences you give them to pass the test?
Okay, challenge accepted. Here is the core of Dr. Ilo's work in 3 beats. We'll make it simple. Beat 1. Before birth, the lungs are full of liquid, and the blood bypasses them completely, relying 100% on the placenta for oxygen.
Okay, lungs are wet and offline. Got it.
Beat 2. The moment the cord is clamped, you cut that life support, which necessitates a rapid, high-stakes switch to using the lungs for gas exchange.
The clock starts ticking.
The clock starts ticking, loud, and beat 3. To make that switch work, you need 3 things to happen simultaneously. You have to clear the fluid from the lungs, you have to drastically drop the blood pressure inside the lungs to let blood flow in, and you have to close the special fetal heart channels that were diverting the blood away in the first place.
Okay. That sounds organized when you say it like that.
Yeah.
Just do these 3 things. But biologically, that sounds like a logistical nightmare to pull off in under 5 minutes.
Oh, it's a massive challenge. In fact, looking at the source text, Dr. Ilo calls it exactly that, a challenge that all humans must undertake to survive.
Undertake to survive. It makes us all sound like action heroes just for making it out of the delivery room.
In a purely biological sense, we are. Every single one of us.
All right, so let's start at the beginning. Section 1, the fetal status quo, the before state. I think this is where we need to break some mental models for people.
Yeah.
Take us inside the womb. What does the cardiopulmonary system actually look like in there? Because I think most people visualize the lungs as these empty pink balloons just waiting to be inflated.
That is the most common misconception, and it's completely wrong. They aren't empty, and they aren't waiting passively. According to the source, the future airways are liquid-filled.
Liquid-filled. So literally, the lungs are full of water. Is it amniotic fluid?
That's a great question. No, it's not amniotic fluid floating in from the outside. The lungs themselves actively secrete this fluid. It's fetal lung fluid.
They make their own fluid.
Yeah. It's essential for their growth and development. The fluid creates a positive pressure, a sort of internal splint that stretches the airways and encourages the cells to grow and differentiate. Without this fluid, the lungs would be underdeveloped or hypoplastic. So they're not just sitting there, they're actively building themselves in this liquid environment.
So functionally, the fetus is drowning.
hmm
If you or I had that much fluid in our lungs.
If you were an adult, yes, you'd be drowning. It would be catastrophic. But for the fetus, it's a functional, necessary state. Dr. Ilo is very clear on this. Before birth, the lungs take no part in gas exchange. None. 0% of your oxygen comes from your lungs when you are a fetus.
That is so strange to wrap your head around. The organ designed for breathing is doing absolutely no breathing. It's just growing.
Precisely. Think of them like a factory that has been built. The machines are installed, the conveyor belts are there, the ventilation system is in place, but the doors are locked, the lights are off, and the entire factory floor is flooded with water.
A submerged factory. I like that.
Or another analogy from the source is a submerged sponge. If you take a dense sponge, hold it underwater, and squeeze it. It's heavy, it's solid, and every little air pocket, every alveolus is filled with liquid. That creates a high-pressure environment inside the lungs.
Okay, but the fetus is alive. It has a heartbeat. It's growing. It's kicking. It needs a constant supply of oxygen. If the factory is closed and flooded, where's the oxygen coming from?
That brings us to what you could call the placenta proxy. The source explicitly states that all gas exchange occurs across the placenta.
So the placenta is the lung. It's not just a feeding tube.
For all intents and purposes, yes. The placenta is the organ of respiration. It's doing the work of oxygenating the blood and removing carbon dioxide. It's essentially an external lung attached to the uterine wall. But it's also the kidney, removing waste, and the digestive system, providing nutrients. It is the ultimate life support machine.
This creates a fascinating engineering problem for the heart and the circulatory system, doesn't it? Because normally the heart's job on the right side is to pump blood to the lungs to get oxygen. But if the lungs are a closed, flooded, high-pressure factory...
Why would you send blood there?
Exactly. Why would the heart waste energy pumping against that pressure?
It wouldn't. It would be a complete waste of energy, and the body is far too efficient for that. This brings us to the hemodynamics. Now, I know hemodynamics sounds like a terrifying medical school word, but let's break it down.
Please do.
Hemo means blood. Dynamics means movement. It's just the physics of blood flow. Where does it go and why?
Dr. Ilo talks about two key variables here in the source, PVR and PBF. These seem to be the main characters in our story today.
They are. They dictate everything. PVR stands for pulmonary vascular resistance.
Okay. Pulmonary meaning lungs, vascular meaning blood vessels, resistance meaning how hard it is to push blood through them.
Exactly. It's a measure of friction or opposition. In the fetus, PVR is high. Very, very high.
And why is it so high? What's causing that resistance?
Well, there are two main reasons. One is simple physics. It's mechanical compression. Remember the submerged sponge? That fluid is physically pressing on all the tiny blood vessels, the capillaries, squishing them.
Okay, so there's less room for the blood to flow.
Right. But two, and this is the more important part, the blood vessels themselves are actively constricted. The smooth muscle in their walls is clamped down tight. This is a physiological state driven by the low oxygen environment of the womb.
So imagine a garden hose, but someone has put a heavy clamp on it.
A very heavy clamp.
Yeah.
Exactly. That creates enormous resistance. Now, basic plumbing physics. If you try to push water through a clamped hose, what happens to the amount of water that gets through? The flow.
It stops, or it becomes a tiny trickle.
Right. And that's the second variable, PBF, or pulmonary blood flow. So because PVR resistance is high, PBF, pulmonary blood flow, is extremely low. Almost none of the blood pumped by the right side of the heart actually goes through the lungs.
Okay, so we have high resistance in the lungs, low flow to the lungs, but the heart is still pumping, right? The right ventricle is churning out blood with every beat. If the main road to the lungs is blocked, where does that blood go? Does it just back up and explode?
No, thankfully not. That would be a design flaw. Nature has built a bypass, a detour, a clever workaround. Dr. Ilo's text highlights a specific anatomical structure called the ductus arteriosus, or DA.
The DA. This is the escape hatch.
It really is. The DA is a short but wide blood vessel that connects the pulmonary artery, which is the road leading to the lungs, directly to the aorta, which is the main highway carrying blood to the entire body.
So it connects the blocked road directly to the superhighway.
Precisely. So the blood leaves the right side of the heart, heads toward the lungs, hits that wall of high resistance, and immediately says, nope, not going that way.
Yeah.
It follows the path of least resistance. It takes a sharp right turn through the ductus arteriosus and merges straight into the aorta, going out to the body,
Skipping the lungs entirely.
completely bypassing them. The source says the majority of the right ventricular output takes this path because, and this is the key, the blood doesn't need to visit the lungs. It's already carrying oxygen that it picked up from the placenta just moments before.
So to recap the before state our baseline, we have lungs that are submerged sponge, making their own fluid to grow. We have blood vessels in those lungs that are clamped tight, creating high PVR.
Right.
We have very little blood actually flowing into the lungs, so low PBF. And instead, the blood is taking a massive detour through the DA to get to the body. And all the while, the placenta is doing all the heavy lifting of respiration.
That is the fetal status quo. It's a perfect, efficient, low-energy system. As long as you are inside the womb, it minimizes the work the heart has to do. It's beautifully adapted.
But then, the lease runs out. Time to move. Which brings us to section 2, the catalyst.
The event of birth. The beginning of the end for that system.
Dr. Elo is very specific about the trigger here. It's not when the head comes out. It's not even when the baby takes its first breath necessarily. It is a specific procedural moment.
Yes. Separating the infant from the placenta by clamping the umbilical cord.
That's the moment the timer starts.
That is the point of no return, the commit point.
Why is that specific moment so critical? Why not when the baby takes a breath? Isn't the breath the important part?
The breath is the solution, but clamping the cord is what creates the problem. Think about it. When you clamp that cord, you have just cut the supply line. You've disconnected the external lung, the external kidney, everything. The oxygen supply from the mom drops to zero instantly.
And waste removal stops.
The carbon dioxide removal stops instantly. CO2 levels in the baby's blood start to rise, making the blood more acidic. This creates a powerful, irresistible urge to breathe.
So clamping the cord is what forces the first breath.
In many ways, yes. The source says this event necessitates the rapid switch to pulmonary gas exchange.
Necessitates. It's not optional.
Necessitates is a polite medical way of saying it's do or die. The metabolic clock is ticking. You have a very limited reserve of oxygen in the blood, maybe a minute or two's worth.
And notice the urgency in the text. It says, within minutes of birth.
Minutes. Think about how crazy that is. Most physiological changes in the human body take time. Puberty takes years. Healing a broken bone takes weeks. Even digesting a meal takes hours. This is a total system reboot that has to complete its core functions in 60 to 120 seconds.
It really puts the pressure on. Dr. Ilo calls it a major physiological challenge. I feel like that's a massive understatement.
It is enormous stress on the system. You are asking an organ system that has been dormant, fluid-filled, and bypassed for 9 months to suddenly become the primary, sole life support system. The factory has to go from flooded and dark to fully operational in the time it takes to make a cup of tea.
Let's dive into how that actually happens. Section 3, the pathophysiology deep dive.
Yeah.
The mechanism of the switch. This is the masterclass part. We need to open the factory.
Right. Dr. Ilo breaks this down into key components. The first one is obvious, but absolutely critical. Aeration.
Lungs expand with air. Sounds simple enough.
Simple on paper, incredibly complex in physics. You have to replace that fluid we talked about with gas. The chest expands, the diaphragm contracts, creating negative pressure of vacuum, and air rushes in. This is that first cry. It's not just a sound, it's a powerful mechanical event. It creates an immense amount of pressure to force those sticky, fluid-filled airways open for the very first time.
But wait, we have a physics problem here. You said the lungs were a submerged sponge. They're completely full of fluid. You can't just put air into a cup that's already full of water. Two things can't occupy the same space at the same time.
Correct. You have to move the liquid to make space for the gas. You can't just ignore it.
So, component 2, fluid clearance. Where does all that water go? Does the baby just cough it all out in one big splash?
Some of it, yes, but not all of it. Dr. Elo is clear that the fetal lung fluid must leave the alveoli. Part of this happens during the birth process itself. The physical squeeze of the birth canal, if you're born vaginally, actually compresses the chest like a tight hug. This forces some of that fluid out of the nose and mouth.
Like squeezing the sponge before you even try to use it.
Exactly. It's a mechanical head start, draining the swamp to build the house, as it were. But that only accounts for a portion of the fluid, maybe about a third. The rest, it has to be absorbed.
Absorbed where? Into the bloodstream.
Into the lung tissue itself, and then into the pulmonary circulation and the lymphatic system. This is a fascinating bit of biology. The cells lining the lungs, the alveolar epithelium, actually switch their function. For 9 months, they were secretory, actively pumping chloride ions and fluid into the lungs to keep them expanded.
They were the ones filling the sponge.
Precisely. At birth, triggered by a surge of labor hormones like adrenaline and cortisol, they flip a switch. They become absorptive. They start actively pumping sodium and, by extension, water out of the airspace and into the lung tissue.
So the baby is literally pulling the water out of the air sacs to make room for the air. It's an active process.
Yes, a very active, energy-intensive process. And if that doesn't happen efficiently, if that fluid stays behind, you have a blockage. Oxygen can't get through a layer of water to the blood vessels. This is actually a common issue in babies born by elective C-section where you don't get that vaginal squeeze.
So they don't get that head start on clearing the fluid.
Exactly. We call the condition transient tachypnea of the newborn, or TTN, basically white lungs. The baby has to breathe really fast tachypnea to compensate for the fluid that hasn't cleared yet. It usually resolves in a day or two as the body slowly absorbs it, but it highlights how important that clearance step is.
That makes so much sense. Okay, so step 1, clear the fluid, partly by a squeeze, partly by absorption. Step 2, pull the air in with that first big breath. But we still have that massive problem from the fetal stage, the high resistance. The blood vessels are still clamped shut.
And this is component 3, the hemodynamic flip. This is, in my opinion, the most elegant part of the entire physiology. It's the magic trick. It explains how the body knows to send blood to the lungs only when they are ready to do their job.
The source describes a major reorganization of the fetal cardiovascular system.
It's a perfect seesaw.
Yeah.
It's a beautiful piece of design. Remember our baseline, fetal state, high resistance leading to low flow.
The clamped hose.
The clamped hose. The newborn state needs the exact opposite. We need low resistance so we can have high flow. We need to open that highway to the lungs.
So how do we release the clamp on the hose? What is the signal that tells those thousands of tiny blood vessels to open up all at once?
The air itself, or more specifically, the oxygen in the air. When that first big breath of air enters the lungs and stretches the alveoli, the oxygen acts as a drug. It is a potent pulmonary vasodilator.
Vasodilator, meaning it widens the vessels.
Correct. The presence of oxygen is the direct signal to the tight, constricted, smooth muscle around the pulmonary arteries to relax. They just let go. The clamp comes off. At the same time, the physical stretching of the lungs from that first breath also helps release local vasodilating substances like nitric oxide.
So it's a combination of the chemical signal from oxygen and the physical signal from the stretch.
Exactly. It's a two-pronged attack on that high resistance. So pulmonary vascular resistance, PVR, drops. And not just a little bit, it plummets drastically within seconds.
And because resistance drops.
Flow follows the path of least resistance. It's just physics. So suddenly, the road to the lungs, which was a blocked, clamped, high-traffic dirt road a minute ago, becomes a wide-open 10-lane superhighway.
And the blood stops taking the detour through the ductus arteriosus.
Why would it? Why take the congested side road when the main highway is completely clear? The pressure in the pulmonary artery drops below the pressure in the aorta. The flow of blood through the ductus arteriosus slows, stops, and can even reverse for a short time. Pulmonary blood flow increases massively, 8 to 10-fold in the first few minutes. The blood rushes into the lungs to pick up that new, abundant supply of oxygen.
It's a self-reinforcing loop. The breath brings the oxygen.
The oxygen opens the vessels.
The open vessels allow blood to flow in to get more oxygen, which keeps the vessels open.
It is an inextricably linked positive feedback loop. You cannot have the blood flow without the air, and the air is useless without the blood flow. It's a synchronized dance that has to be perfect. This is what we call ventilation-perfusion matching. You're matching the air with the blood.
This leads us perfectly into section 4. Now that we understand the mechanism, Dr. Ilo outlines the 3 principles of conversion. It's almost like a checklist for survival. If you are a doctor or a midwife holding a newborn, these are the 3 boxes you need to check in your head to know the transition is working.
Yes. The source lists the conversion of the fetal to adult circulation requires, and then gives us 3 bullet points. These are the 3 pillars of the transition. They have to happen in the right order.
Okay, let's go through them one by one.
Okay.
Requirement number 1, elimination of the umbilical placental circulation.
We touched on this. This is the clamping of the cord. It shuts down the old life support system. It's step 1. But it does one more crucial thing hemodynamically. It raises the baby's systemic blood pressure.
Why does it do that? I don't quite follow.
Think of the placenta as a giant, low-resistance release valve for the circulatory system. It's a huge vascular bed where blood can flow very easily. It's like having a big open tap in your home's plumbing system. It keeps the overall pressure low.
Okay, pressure leak almost.
You can think of it that way. When you clamp the cord, you plug that leak. You remove that massive low-resistance circuit. All of that blood is now confined to the baby's body.
So the pressure in the rest of the pipes, the baby's systemic circulation has to go up.
Exactly. Systemic vascular resistance rises sharply, which is a good thing. We need that high pressure to pump oxygenated blood against gravity up to the brain and out to the fingers and toes. You want your systemic body pressure to be higher than your new low lung pressure. This pressure difference is what helps close some of the fetal shunts.
So step 1, remove the placenta, pressure in the body rises. That makes sense. Requirement number 2, increase of pulmonary blood flow.
This is the result of what we just described with the vasodilation. The source says flow must rise to a level necessary for adequate gas exchange.
I want to pause on that phrasing. To a level necessary. Why that specific wording? It sounds very precise.
Because it's not about just flooding the lungs with blood, it's about balance. This is that concept of ventilation perfusion matching, or VQ match. It's one of the most fundamental principles in respiratory physiology.
Explain that a bit more.
Okay, imagine you have a part of your lung that is getting lots of air, ventilation, but only a tiny trickle of blood, perfusion. That's wasted ventilation, or what we call dead space. The oxygen is there, but nothing is there to pick it up and transport it.
A train station with no passengers.
Perfect analogy. Now, the opposite. Imagine a part of the lung that has lots of blood flow, but no air getting to it, maybe because of fluid or a blockage. That's a shunt. The deoxygenated blood just flows right past without picking up any oxygen, goes back to the body.
A train full of people that skips a station.
Exactly. For life to work, you need the flow to rise specifically to the level that matches the air intake. The amount of air and the amount of blood have to be perfectly matched in every tiny part of the lung. That match is what allows for efficient, life-sustaining gas exchange.
Fascinating. It really is a balancing act. And that brings us to requirement number 3. Separation of the heart sides by the closure of fetal channels.
This is the final seal on the deal. This is what turns the fetal circulation into the adult circulation. The text mentions closure of fetal channels. We've already talked about the main one, the ductus arteriosus.
The detour road.
Right. So 2 things happen to close it down, functionally at first and then permanently. First, the flow dynamics change. We said the pressure in the pulmonary artery plummets. It's now lower than the aorta, so the blood no longer wants to flow from the pulmonary artery to the aorta. The incentive is gone.
The path of least resistance has changed.
It is completely flipped. But secondly, and this is so clever, the ductus itself reacts to the new environment. The higher levels of oxygen in the blood cause the smooth muscle in the wall of the ductus arteriosus to constrict. It clamps itself shut.
Wait. You said a minute ago that oxygen makes the lung vessels open.
I did.
But now you're saying oxygen makes the ductus arteriosus close.
Yes. Isn't that incredible? The same molecule oxygen has the opposite effect on 2 different blood vessels that are literally millimeters apart.
How is that possible?
It's brilliant biological coding. The cells and the receptors in the pulmonary arterioles are programmed to react one way to oxygen, and the tissue in the ductus is programmed to react the opposite way. Oxygen is the universal signal that means the system is live, and it tells the body, open the lungs and close the bypass at the exact same time.
And what about the separation of the left sides of the heart? The text says separation of the left sides, but I assume it implies separating the right and left sides from each other.
Yes, that's what it means. It's about separating the blue blood from the red blood. In the fetus, because of the shunts, the blood is always mixing. It's all kind of a shade of purple. There isn't a truly separate pulmonary and systemic circuit.
But we need that separation in an adult.
We need strict segregation for efficiency. Blue blood, deoxygenated from the body, stays on the right side of the heart and goes only to the lungs. Red blood, oxygenated from the lungs, stays on the left side of the heart and goes only to the body. Never the twain shall meet. Closing the ductus arteriosus is one part of that. Closing another hole, the foramen oval between the atria, is the other. That closes due to the pressure changes too.
It's amazing that this happens automatically. No one tells the heart, hey, close that valve now. It just responds to the new pressures and the new oxygen levels.
It is purely response-driven physiology. The environment changes, air enters, placenta leaves, and the anatomy responds. Vessels open, shunts close. It's pure physics and chemistry driving the whole thing.
So we've covered the fetal state, the event, the mechanism, and the checklist. What does this all mean for us? This takes us to Section 5, High-Yield Pearls and Clinical Relevance. The title of Dr. Elo's work is Cardiopulmonary Changes at Birth and Principles of Newborn.
Principles of newborn, that's the key. This isn't just abstract science.
Right. How do these biological facts dictate how we actually care for a baby in those first few minutes?
Well, if you understand that the transition depends on these three things, aeration, fluid clearance, and the hemodynamic flip-flop, then newborn resuscitation becomes very logical. It stops being a ritual and starts being a scientific intervention. You know exactly what you're trying to achieve.
Give me an example. Let's make it practical.
Okay. Why do we dry and stimulate a baby immediately after birth? It seems so basic. We aren't just cleaning them or warming them, though that's part of it. The physical sensation of being rubbed vigorously with a towel stimulates the respiratory drive centers in the brainstem. It provokes that first gasp and cry.
So we're trying to kickstart aeration.
We are trying to mechanically and neurologically induce aeration. We want that cry. We need that pressure to pop open the lungs and start the whole cascade.
And if they are born and they're a bit floppy and gurgling?
We suction the mouth and nose.
Yeah.
Why? To assist with fluid clearance. To help remove that physical barrier so the air can get in. If the airway is blocked, nothing else matters.
And why is that first minute, what they call the golden minute, so critical? Why the urgency?
Because we are on the clock waiting for that pulmonary resistance to drop. If a baby comes out and stays blue and limp, it usually means that PVR is staying high. The blood vessels in the lungs aren't opening. The switch isn't flipping.
So their circulation is stuck in the fetal pattern.
Exactly. We call it persistent pulmonary hypertension of the newborn, or PPHN. The baby is out of the womb, but their heart and lungs think they're still inside. The blood keeps taking the old bypass route through the ductus arteriosus, skipping the lungs, and so the baby can't get oxygenated.
So knowing this physiology tells the doctor exactly what to do.
It tells them everything. The baby needs help with the transition. So what do? You give positive pressure ventilation, you give oxygen. You're trying to manually force aeration and deliver that oxygen drug to the pulmonary vessels to convince them to open up. You have to break that vicious cycle of high resistance.
The medical protocols make so much sense. You aren't just following a rule book. You're responding directly to the underlying physiology.
Exactly. You are trying to manually assist the checklist that nature's supposed to be running on its own. Your interventions map directly onto those three principles of conversion.
Here's where it gets really interesting to me. We were discussing the source material earlier, and you mentioned looking at a specific image in Dr. Yellow's paper, the one with the diagram of the fetal alveoli and the constricted blood vessels. You called it an aha moment.
Yes. There is a diagram in the source, a simple line drawing. It shows the fluid-filled alveolus, and next to it, it explicitly labels constricted blood vessels. And for some reason, that image it clicked for me in a new way. I found that image profound.
Why? What was so profound about it?
Because it represents potential energy, stored tension. Think about it. For 9 full months, the entire respiratory vascular system is clamped down. It's tight. It's under constant tension. It's actively resisting flow. It is not a relaxed, passive state. It is a coiled spring.
So it's an active process to keep it closed.
A very active process. And that first breath is what releases the tension. It's a biological metaphor for the release of potential into life. We are built to be under pressure, to be restricted, until the precise moment we are ready to breathe. The restriction exists so that the release can be powerful and instantaneous.
That is poetic. It's like the bow's drawn back for 9 months, and the moment of birth is letting the arrow fly.
Beautifully put. And without that tension, without that high PVR baseline, the transition wouldn't work. You need the contrast. You need that massive pressure drop to pull the blood into the lungs. It's the differential that drives the whole system.
Let's wrap this up with a final summary. If you had to put the before and after on a cheat sheet for our listeners, just to lock it in, what does it look like?
Okay, the cheat sheet. This is the whole deep dive on a napkin. They are fluid-filled. That's the submerged sponge.
Pulmonary resistance is very high. That's the clamp toes.
It's bypassing the lungs via the ductus arteriosus and the boss. The placenta does all the work.
Okay, that's the before. What about the after, the newborn? Newborn.
They become air-filled.
Pulmonary resistance plummets. It's low. The open highway.
Now it's flowing to the lungs, with the left and right sides of the heart separated. And the new boss. The lungs are now in charge of respiration.
Simple, yet it changes everything.
It changes absolutely everything in about 90 seconds.
So what does this all mean for you, the listener? Why should you care about pulmonary vascular resistance and the ductus arteriosus?
Because understanding this transition explains why the first few minutes of your life were the most critical minutes of your entire existence. It explains why when a baby is born, the entire delivery room goes silent for a moment, waiting. They're waiting to hear that cry.
It's not just a sound.
That cry isn't just noise. That cry is the sound of physics. It's the sound of aeration happening. It's the sound of resistance dropping. It's the sound of the switch flipping. It's the sound of the physics of life taking over from the physics of the womb.
And it's the sound of you surviving the most dangerous thing you've ever done. Absolutely.
Yeah.
You navigated the bypass, you cleared the fluid, you absorbed the water, you flipped the switch, you made it. You did all of that before you were even consciously aware of anything.
We have just completed a masterclass on the transition of birth. We hope this gives you a new appreciation for the engineering inside your own chest right now that's been working perfectly ever since.
It truly is a miracle of mechanics and biological programming.
I want to leave you with one final thought to mull over. We talked about how that fetal lung fluid leaves the lungs. We said a lot of it doesn't get squeezed out. It gets absorbed into the body.
Right, into the lung tissue and the circulation.
So think about that. That means, in a way, the very water that filled your lungs and nurtured their growth inside the womb. It didn't just disappear. It was absorbed into your blood.
Right.
It became part of your hydration. It became part of your plasma volume in your first moments of life.
Huh. I've never thought of it that way.
You literally drink your own past to survive your future.
That is a fascinating and very cool perspective.
Big thanks to the work of Dr. Kenechukwu Keilo for providing the roadmap for this deep dive. And thank you, as always, for listening.
Take care.
See you next time on The Deep Dive.